BJT amplifiers. Welcome back to Bias Point, where we uncover the rhythm of electronics one concept at a time. In our last chapter, we explored transistor biasing, the all-important tuning stage for every amplifier. Now that our transistors are properly set, ready to perform, it's time to let the music play, as I would say. So in this episode, we're diving into BJT amplifiers, how they work, why they matter, and how tiny signals become powerful voices in the circuits that we build. So whether you're designing audio gear, sensors, or analog front ends for like digital systems, BJTs will still hold their place in the spotlight. And the better you understand how to amplify a signal cleanly, linearly, and with control, the closer you get to mastering electronics. So let's get started with the basics. What exactly does a BJT amplifier do? And why is biasing just the beginning of the story? Talk about small signal amplifiers from DC to dynamic. Let's connect the dots. So in our previous episodes, we talked all about biasing a transistor. And you might have noticed something. All of that was purely DC. So setting the cue point was about getting the transistor into a ready state, a kind of electrical meditation, calm, stable, focused, ready to go. But now we add movement. So this is where small signal amplifiers come in. These circuits take tiny, wiggly AC signals from a microphone, an antenna, or some sensor, and it boosts them without distortion. And the key point acts like the transistor's resting position. When an AC input signal arrives, it causes the current and voltage to swing slightly around that point, not wildly, but just enough to represent the original waveform. So you have small signal amplifiers, which are all about precision. The changes in voltage and current are small, but they're meaningful. Think of a whisper picked up by a microphone, for example. So the circuit's job is to amplify that whisper without shouting or losing tone. And that's the magic. By biasing correctly, we allow the transistor to respond gently and linearly to even the smallest input. Quantities right in the wave. Now that we've set our cue point and introduced small signal amplifiers, let's look at what's actually happening with the signal, the AC quantities. In amplifier circuits or amplifier analysis, AC signals, they're all about change. They ride on top of the steady state DC bias. And what we're really watching is how the collector emitter voltage varies over time. So in the graph shown here, you'll see the output waveform swinging around a fixed point. That's our cue point voltage, V sub CE. And the curve represents the amplified AC signal. And the important thing is that it stays centered, avoiding cutoff at the bottom and saturation at the top. We often describe these signals using RMS, the root mean squared values. That's like the effective strength of the signal. Or we refer to average or peak values depending on the context. And to keep track of all of this, we use a naming convention. So lowercase letter with a subscript like little v c sub e or little c sub e. This means AC quantity. Uppercases like capital V sub, capital C, capital E. That usually refers to DC operating points. Um, so this is the way the naming convention should be. Just because you see it written down, that don't assume that the person who wrote it meant it this way. I see people interchanging these lowercase and uppercase and not representing what they're supposed to represent, in other words. So, but this is the way you're supposed to represent them. Um, Understanding these AC variations, this is the key to mastering amplifier behavior. It's the difference between just biasing a transistor and actually making it perform. Linear amplifier, a mirror, not a megaphone. Okay, so far we've explored how transistors respond to AC signals, and now we turn our focus to the ultimate goal, which is linear amplification. So what is a linear amplifier? Well, this is a precision mirror. It doesn't just make the signal louder, it preserves its shape. Every rise and fall in the input waveform is echoed at the output, just a little bit larger. And that's the beauty of operating in the linear region. We spent so much time that we bias for. It's really important that we bias for this. In the example circuit you see, you're going to notice something interesting. The input and output waveforms are inverted, meaning the output is flipped vertically, but their shapes match exactly, right? So this is a signature of a common emitter amplifier, which introduces a 180-degree phase shift. So current through the collector increases when base current increases, which causes voltage across the RC to rise, but that makes the VCE drop, and that's where we get the inversion. It goes in the opposite direction. So as long as we stay within the limits of the transistor's linear region, that inverted signal is a faithful replica of the original. And that's the goal. No distortion, no clipping, no lost information, just clean, consistent amplification. Load line, a moving target. So earlier we talked about the DC load line, which sets the stage for the transistor's quiescent operating point, the Q point. But once we introduce a real AC signal, the story shifts. And we draw a new AC load line. And here's what's happening. Capacitors in the amplifier circuit block DC, but they pass AC signals. So even though the DC load line is based only on static resistor values, the AC signal sees a different landscape, one where capacitors behave like short circuits and add new paths for current flow. So the result, the effective load resistance seen by the AC signal is different, usually lower, because the collector resistor and the load resistor appear in parallel to AC. So this changes the slope of the load line when we graph collector current, I sub C, versus the collector emitter voltage, V sub CE. So instead of staying confined to the original DC slope, the transistor now moves along a steeper AC load line, and that allows greater swing in voltage and current. So it's like the stage expands when the music starts. More room for the signal to move, more gain, greater responsiveness, and as long as the swing stays within the linear boundaries, the signal comes out strong and undistorted. Transistor AC models, looking inside the machine. So far we've been talking about how a transistor behaves. Now let's dig into why it behaves that way. The psychology of the transistor. I'm just kidding. Um, I study engineering psychology, but not to that type of degree. So what do? We need a model, a simplified version of the transistor that captures its electrical behavior, especially during AC operations. So just like a mechanical engineer might use a spring and a mass model to describe a suspension system, we use AC models to describe a transistor's small signal performance. So these models let us break the transistor down into components like resistors and controlled current sources, and that responds to voltage changes. So there are two main types of AC models. The R parameter model, this is in every textbook. It's based on internal resistance, and the H parameter model, also called the hybrid model, that's where H comes from, which mixes voltage and current behavior. So the R model is simple, it's intuitive, it's great for conceptual learning and hand calculations. The H model is more comprehensive, uses in data sheets and more advanced analysis, especially for real world transistors with mixed behavior. So these models aren't just for textbooks. They're how we calculate gain, input impedance, output resistance, and bandwidth. So in other words, they turn your amplifier from a black box into a transparent, tunable machine. R parameters, the resistance view of a transistor. Okay, now that we've introduced transistor AC models, let's zoom in on one of the simplest and most intuitive, which is the R parameter model, or what we sometimes call the resistance model. So this model treats the transistor as a set of small resistances and a current controlled element that helps us understand how signals move and how gain is generated. And here's how we break it down. So we have the AC alpha, right, or the alpha sub AC, and this is the ratio of collector current to emitter current, and it's very close to 1 in most BJTs. Then we have beta, the AC beta, and this is the familiar current gain, right? We have I sub C over I sub B. Then we have the R prime E, which is the AC emitter resistance, and this is the key player. It's small and it controls the gain of the amplifier, and it's given by R prime E is equal to 25 millivolts divided by I sub E, right, the DC current. That 25 millivolts comes from the thermal voltage at room temperature. So the higher the emitter current, the smaller this resistance, and the higher the gain. Then we have R prime B. This is the internal base resistance. It's usually very, very low. Then we have R prime C. This is the internal collector resistance. This is typically very high. And it's often ignored in small signal analysis. This model is especially useful for common emitter amplifiers, where gain is roughly R sub C over R prime E. So knowing your emitter current gives you a direct handle on how much amplification you can expect. This is pretty straightforward. It's a nice way to link circuit behavior to transistor physics or transistor psychology. I'm kidding, kidding. And it's the foundation of quick, practical amplifier design. The common emitter amplifier, classic power with inversion. So if there's one BJT amplifier configuration you need to master, it's the common emitter amplifier. And we often refer to this as the CE amplifier, right? Common emitter. So in this setup, the input signal is applied to the base and the output is taken from the collector. The emitter is shared or it's common, right? It's a common terminal. It's grounded for AC through a bypass capacitor. And that's why it's called common emitter. What makes the common emitter amplifier so widely used? With two big things. One, it has signal inversion, and two, it has a high voltage gain. And we'll learn about the advantages and disadvantages of the other uh, amplifier circuits as well. But let's start with just this one. So signal inversion. So that means that the output voltage is an inverted version of the input. So when the output, when the input swings up, the output swings down, and vice versa. When the input swings down, the output swings up. But the shape of the waveform remains intact. So that's because it's linear amplification in action. Then we have this particular circuit also has high voltage gain. Thanks to the relationship between collector resistance, the R sub C, and the small emitter resistance R prime E. Right? So common emitter amplifiers can produce significant amplification even from a tiny input signal. So this configuration is like the main workhorse of most analog electronics. So from audio preamps to sensor signal boosters, common emitter amplifiers are everywhere because they're simple, they're powerful, and they're easy to tune. And just like a good conductor in an orchestra, the CE amplifier keeps everything in phase, just flipped upside down. Inside the CE amplifier, what makes it work? So let's take a closer look at how the common emitter amplifier is wired and why each part matters. So this configuration uses a voltage divider bias. Um, we've covered this before to set the base at a steady DC level, the transistor's key point, right? Um, we have to design this, but now we introduce three key capacitors to this circuit. Right? We have C1 and C3, which you'll see in the diagram. They're called coupling capacitors. And again, you'll see this on the diagram in the next slide. They act like gates. They allow AC signals through while blocking DC. Like C1 couples the input signal to the base, and C3 couples the amplified signal from the collector to the load. So like a speaker or the next stage of the amplifier. C2, that's the bypass capacitor across the emitter resistor. Its job is to short AC signals to ground at high frequencies, so effectively removing RE from the AC path. And what that does is it boosts the gain because it eliminates the emitter's feedback effect for AC while still providing DC stabilization. So this setup allows the input signal to swing freely at the base and for the output signal to reflect that swing, again, but inverted, at the collector. So the amplifier output is 180 degrees out of phase with the input, just like we'd expect from a CE configuration. And remember, the emitter is common to both input and output. That's why we call it common emitter amplifier. And because of the bypass capacitor, there is no AC signal left at the emitter during operation. So the result is you have clean amplification, phase inversion, and high voltage gain, all with excellent bias stability. Okay, phase inversion, which is the signature of the CE amplifier. Let's wrap up our exploration of the common emitter amplifier by talking about one of its most distinctive features, and that's phase inversion. So in a common emitter amplifier, the output signal is 180 degrees out of phase with the input. And that means whenever the input voltage goes up, the output voltage goes down, and vice versa. But why does this happen? And it all comes down to the flow of current. When the input voltage rises, it causes an increase in base current because the transistor is biased in its active region. This also increases the collector current. So now here's the key part. That increased collector current flows through the collector resistor, R sub C, and causes a larger voltage drop across it. And if more voltage drops across R sub C, then the voltage at the collector must drop. So remember, it's just a reference to VCC. R sub C drops more voltage, meaning like a voltage divider, you have less at the voltage at the collector itself. So a rising input actually pulls the output voltage down, and that's where the inversion happens. So it's not magic, or it is. It's engineering magic. Yes, it's engineering magic, and it's also math and physics, which is how we develop engineering magic. Math and physics working together through Ohm's law and transistor action. So this phase reversal is the signature behavior of the common emitter amplifier. And while it may seem like a drawback at first, it's actually useful in multi-stage designs where inversion is needed or can be corrected later on. So just imagine you invert it once, but you need it in its original shift. So you just invert it again with a second stage. And that's it for this slide. DC analysis, let's clear the stage. So before we can analyze how a transistor amplifier responds to signals, we have to understand how it behaves at rest. And that's where DC analysis comes in. To perform DC analysis, we remove all of the AC related components, which are the coupling capacitors and the bypass capacitors. Why? Because capacitors act like open circuits to DC, so they block steady state current. So for the purpose of DC, they don't exist in the circuit. We also ignore the AC signal source and the load resistors. Those only matter when signals are present, and what we're left with is biasing network resistors R1 and R2 that set the base voltage. We have RC at the collector and RE in the emitter, along with the transistor itself. So this simplified view lets us calculate critical values like the base current, collector current, and the collector emitter voltage. Now, all this defines the key point. Remember that without this DC foundation, there is no meaningful AC amplification. So think of it like tuning an instrument before the concert. DC analysis sets the stage. Only once that's done, then you can actually begin the music. Then the signal can begin transmitting. Okay, DC analysis by the numbers. Let's take everything we've just learned about DC analysis and walk through a real example. This is where theory meets calculations. We've got a transistor with a voltage divider bias using R1 being equal to 68 kiloohms, R2 is equal to 27 kiloohms. It's connected to a 15-volt power supply. The emitter resistor R sub E, that's 2.2K, and the collector resistor RC, R sub C, is 3.9K kiloohms. All right, so step one, we want to calculate the base voltage. We can use the voltage divider formula, where VB is going to be equal to that ratio of the resistance for the voltage divider, so 27K divided by 68K plus 27K, right? Times the source voltage, which is 15 volts. And this is going to give us that ratio that's going to be seen there at the voltage divider. First, it's 4.26 volts in this case. So we have 4.26 volts on the base. Okay, now we need to calculate the emitter voltage, V sub E, and we can use a KVL, where VE is equal to V sub B minus VBE. So we calculated VB to be 4.26. We know that the voltage from base to emitter, which is that depletion region junction voltage, is 0.7 volts. So 4.26 volts minus the 0.7 volts will give us 3.56 volts at the emitter. And again, we're using Kirchhoff's voltage law, so this has to jive. The next step will be to calculate the emitter current. So we can use Ohm's law here. We have the voltage across the emitter. We have the resistance of the emitter. So current is voltage divided by resistance. 30.56 volts divided by 2.2 k ohms. That gives us 1.62 milliamps at the emitter. And now we're going to make one small assumption here in the DC biasing, that the I sub C and I sub E are extremely close together as far as values, minus a tiny I sub B current that's going to the base, right? So they're approximately each other. So we can go ahead and, for now, for the sake of simplicity, make I sub C also equal to 1.62 milliamps. And that we make, based on that assumption, we go to the next part, which is finding the collector voltage, right? So the collector voltage is going to be equal to the source, which is VCC, minus that collector current times the collector resistor. So I sub C times RC. That's going to be 15 volts minus, and then 1.62 for collector current times 3.9K resistance. That's going to give us a voltage that we subtract from 15, and we should end up with, like you see on the slide, 8.68 volts at the collector. Again, this is not the voltage at the collector resistor. This is at the collector point. So now we want to find voltage from collector to emitter, so the voltage across that transistor. So VCE is equal to VC minus VE, which is going to be equal to 8.68 volts, which is at the collector, minus 3.56 volts, which is at the emitter. And the difference between those two is 5.12. So that's the voltage we have across that transistor. And we'll leave it there for this slide. I want to thank you very much. Let's go ahead and move on to the next slide. AC analysis, signal in motion. So with DC analysis complete and the transistor properly biased, it's time to let the signal flow. So that means shifting to AC analysis, where we focus on how the amplifier responds to time variant inputs. To analyze the AC behavior, we treat capacitors very differently. So at signal frequencies, they act like short circuits because their reactance X sub C approaches zero. So in our analysis, coupling and bypass capacitors are replaced with wires. We also replace the DC supply VCC with the ground, but not just any ground. It's called AC ground because the VCC provides DC power. No AC signal develops across it. So it remains constant from AC perspective, and that's why we write it this way. Uh, so this is going to dramatically simplify the circuit. We strip it down to only the elements that affect the signal, which are the resistors, transistors, being small signal modeling, and the AC paths. So for example, in this setup, the emitter is shorted to ground via the bypass capacitor, and the bias network resistors remain, but the power supply and the signal source, those are grounded. So this cleaned up version is what we use to calculate voltage gain, input impedance, and output impedance, which are the key specs that tell us how well our amplifier will perform in the real world. AC analysis, what the signal sees. Now that we've set up the AC model of our amplifier, let's ask a fundamental question, and that question is this. What does the signal source see when it looks into the amplifier? When it looks into the amplifier's beautiful eyes. Okay, that just made it weird. Let's keep on going. So that's where input resistance comes in, right? That's where we see it. So an AC voltage source V sub S is connected to the amplifier's input. The amount of signal that reaches the transistor's base depends on the total resistance seen at that input. So if the source has zero internal resistance, then the entire signal appears at the base, which is the ideal case. But in real life, we have to consider more. So here's what matters. RS, the source resistance, or R sub S, which is the source resistance, which we'll often assume to be zero for ideal cases, but it actually is a very small amount. We have R1 and R2, the biasing resistors that are still present in the AC model. We have the base resistance or the input resistance, R sub N, and that's the internal resistance looking into the base of the transistor, which depends on the beta of the transistor and the R prime E. So the total impedance or the total input resistance, excuse me, not impedance, but the total input resistance is going to be R sub n total equal to R1 in parallel with R2, which is in parallel with the input resistance, which is the input resistance at the base, seen at the base. So this total resistance determines how much of the input voltage actually makes it to the base. If it's too low, much of the signal drops across the source, and that means poor performance. So just like a musician needs a quiet room to be heard, your amplifier needs a properly matched input to hear the signal clearly. AC analysis, the metrics that matter. So let's close out our amplifier series with the three most important performance parameters: the input resistance, output resistance, and voltage gain. So these tell us how the amplifier interacts with the rest of the system and how much punch it delivers. Input resistance, or the R sub in at the base, this is what the signal sees at the transistor base. It depends on the transistor's current gain, which is that beta, the AC beta, and the small signal resistance, which is R prime E. So the input resistance, R sub in at the base, is equal to beta, AC beta, times R prime E. Let me repeat that again. Beta times R prime E. Or if there's no bypass capacitor, so the input resistance at the base would be the AC beta times the addition of those resistors, the R prime E plus R sub E. Right? Without the bypass capacitor, uh, R sub E will be present all the time. With the bypass capacitor, right, at high frequencies, it gets shorted out to ground, so you short out RE. What this does is this value affects how well the input signal is transferred from the source. Then we have the output resistance, R sub out. Yeah, for most single stage BJT amps, this is usually R out is going to be equal to R sub C. Or R sub C in parallel with R sub L, the load resistor, if there's a load resistance present. Um, and what happens is this determines how well the amplifier can drive a load. So lower output resistance is usually better. We have the voltage gain, A sub V, and this is a big one. So how much the amplifier increases signal voltage? A sub V is going to be equal to the ratio of R out divided by R prime E, or if the emitter resistor R sub B, if that's not bypassed, then it's the addition of both of those emitter resistances. So the gain would be R sub out divided by the addition of R prime E plus RE. It's going to change the number slightly. So you'll see why bypass capacitors matter. Without them, the emitter resistor reduces the gain. But with them, gain increases. And if you remember that R prime E is calculated from DC analysis, where R prime E is equal to that 25 millivolts divided by I sub E. The effect of load when the real world connects. So we've analyzed the amplifier in isolation, but in real life, it doesn't operate alone. It drives something, a speaker, a sensor interface, or another circuit. And that's where the load comes in. When you connect a resistor, R sub L, to the output through a coupling capacitor, you're adding a load to the circuit. And this changes how the amplifier performs. Specifically, it changes the output resistance that the signal sees. Originally, we said that R sub out is equal to R sub E, right? Just a collector resistance. But once R sub L is connected, once we connect some load, it forms a parallel combination with R sub C. So the output resistance, the load resistance, not the load resistance, the output resistance, R sub out, with a load would equal R sub C in parallel with R sub L. And what this does, it reduces the output resistance depending on the values. It can also reduce the voltage gain because gain is directly tied to that R sub out. So even though you might have calculated a beautiful high gain on paper, the real gain drops when the load is applied. It's a reminder that everything is connected. Your amplifier doesn't just amplify in a vacuum. What you connect to it matters. So always factor in the load because it shapes the final sound signal or behavior. Bypass capacitor, hidden hero of gain. So let's end with a powerful and often underappreciated component, the emitter bypass capacitor. And it may look small, but its impact on voltage is massive. So in our common emitter amplifier, we've got an emitter resistor, R sub E, which improves stability, but it also reduces gain. That's because it adds negative feedback as current increases, voltage across the RE rises, pushing back against the base emitter junction. Then enter the bypass capacitor. When placed across R sub E, it effectively short circuits that component for AC signals. So it removes it from the gain equation while still keeping the DC benefits for biasing. So let's go ahead and compare. With bypass capacitor, the voltage gain is going to be equal to R sub C divided by R prime E. High gain, since only the R prime E is in the denominator. Without the bypass capacitor, you have to include the emitter resistance now. So the gain would be A sub V is equal to R sub C divided by the sum of the resistances, which is R sub E plus R prime E. All right, you're going to have lower gain since you're dividing it by more. So if you want maximum voltage gain, the bypass capacitor is your secret weapon. But if you want a more stable amplifier with less distortion and a wider bandwidth, sometimes leaving it out is the right move. But the bottom line is the voltage gain is reduced without the bypass capacitor, but you may do that by design. And I want to thank you very much. This is the end of this session, and I will see you in part 2.